Thousands of feet below the surface, the deep ocean is home to a visual paradox: distinct underwater lakes. These pools are characterized by a visible, rippling surface and a clearly defined shoreline, sitting entirely unmixed at the bottom of the sea. The fluid inside is so much denser than the surrounding water that it creates a physical barrier. Scientific instruments and submersibles don't simply sink into these pools. They bounce off the surface as if they've hit a solid floor. To an unadapted animal, like a deep-sea fish, the edge of the lake looks like a typical staging ground. But crossing that rippling boundary is a fatal mistake. The transition into the brine triggers immediate toxic shock. As the oxygen-free liquid enters their systems, the animals suffer from instant cerebral hypoxia. Their bodies sink to the bottom, where the total lack of oxygen halts the natural process of decay. Because nothing can rot in this environment, dead creatures accumulate in a perfectly preserved state for years, forming a literal graveyard on the lakebed. In a dynamic ocean where currents are constantly mixing, the existence of a stagnant, highly toxic body of water is a geological anomaly. To understand how these death traps are physically possible, we have to look past the water and into the history of the Earth's crust. These pools are essentially the ghosts of ancient seas that evaporated millions of years ago, leaving behind massive layers of salt that were slowly buried by the ocean floor. In the Gulf of Mexico, these Jurassic-era salt beds were buried under thousands of feet of heavy sediment. The weight of the overlying rock eventually squeezes the less dense salt upward. It deforms into domes, eventually breaching the seafloor and dissolving into the seawater above. However, in the Red Sea, the same result is achieved through a different process: the literal tearing of the Earth's surface. Here, the African and Arabian tectonic plates are pulling in contrary directions, creating deep depressions and exposing the water to intense geothermal heat. In the Atlantis II Deep, this geothermal activity is so intense that the water temperature at the bottom of the rift spikes to over 68 degrees Celsius. This diagram illustrates the resulting structure. Whether formed by salt domes or tectonic rifts, the heavy, mineral-rich fluids settle into these steep-walled basins, where they are trapped by their own weight. From these cracks in the crust, the Earth is actively injecting an alien chemistry into the deep ocean. This injection creates a brine that is roughly 5 times saltier than the surrounding sea. Because this liquid is so incredibly heavy, it is physically unable to mix with regular seawater. It simply pools in the craters, forming the underwater lakes we see from submersibles. Alongside the salt, the pools are packed with deadly concentrations of hydrogen sulfide and methane gas. The extreme density of the fluid also makes it anoxic. Oxygen cannot penetrate the surface of the pool, leaving the water inside completely suffocating to any respiring animal. It is this combination, the toxic gases, the hypersalinity, and the total lack of oxygen, that creates the perfectly preserved underwater graveyard. But while the center of the lake is a dead zone, the shoreline is often teeming with life. The perimeter is dominated by dense beds of specialized mussels. These are the biological architects of the pool's edge, thriving exactly where the toxic brine meets the ocean. These mussels survive through a symbiotic relationship with internal bacteria. The bacteria take the lethal methane gas venting from the pool and convert it directly into a functional carbon sugar, providing food for the mussel. Just above the brine surface, patchy reddish layers are often visible. These are colonies of halophilic archaea, microbes that have evolved to utilize the extreme salt gradient as an energy source. This entire ecosystem exists in total darkness, completely divorced from the sun, and powered exclusively by the lethal chemistry of the brine. Higher up the food chain, scavengers like border shrimp wait along the interface, plucking out the stunned animals that accidentally drift into the toxic water. But the most specialized survivor is the ancient hagfish, which has developed a way to enter the dead zone on purpose. When threatened or stressed, the hagfish ejects protein threads that expand into massive clouds of slime, a single teaspoon of material becoming a bucketful in seconds. This mucus coating reduces the exchange of water across the hagfish's skein. This temporary shield allows them to tolerate brief contact with the hypersaline brine, letting them dash into the pool to scavenge dying animals before retreating to the safety of the ocean. It is a survival strategy shaped entirely by the chemical boundary of the pool. The existence of these pools proves that life's boundary isn't fixed by oxygen or light. By evolving to exploit a concentrated cocktail of methane and salt, these organisms show that even the most toxic environments on our planet can be claimed and colonized.